Thank you very much, Harry. I'd like to thank for the invitation, and also I'd like to thank the hospitality, also Professor Ko as well. Thank you. And okay, also I'd like to say congratulations for the victory. I watched it, the game, preparing the talks. Nothing happened until the end, but yeah, I like to share the happiness with you. Yeah, thank you. So I'm going to give 4 talks, 2 talks today and two more talks tomorrow. But for the first talk, I like to use slides to give you a kind of overview of these 4 lectures. So today I start with something elementary, but also I try to state kind of 1 or 2 main theorems, which I try to explain later in those 3 lectures about proofs. So so feel free to ask questions. So this talk is going to be a little bit like a colloquium talks. I don't know if you have ever been to a colloquium talk, so it's kind of for a general audience, for the math audience for the beginning. Okay. Oh, I see. So can I? It doesn't matter. Okay, so let me start with hyperbolic plane. You have seen hyperbolic plane this week, so H2, and then I chose this upper half plane model to define it or explain what it is. So you take upper half plane in the Euclidean plane above the x-axis, not containing the x-axis because y is really positive, and then but the metric it's a Riemannian manifold, but the metric is not Euclidean. So I wrote down the metric here. So it's different from Riemannian metric by a factor depending on each point, which is y. So some people say this is a conformal change of the Euclidean metric. So if you are higher, namely if y coordinate is large, then the metric or distance or whatever shrinks by the factor of 1 over y. So that's the new metric. On the other hand, if you approach the x-axis, y goes to 0. That means the distance there is much larger than compared to the Euclidean distance. Okay, and then I didn't draw. I just found this file somewhere on the web. So those lines, so vertical lines, and also these half circles are geodesics for those for this new metric, hyperbolic metric, and they are. Okay, I didn't draw all of them, but they are the set of geodesics. So any vertical line and any this half circle is a geodesic. So you can see that if you have any 2 points in the upper half plane, you can find one geodesic from this picture. And also you can say that the geodesic joining given 2 points is unique because there is only one possibility, either a vertical one or this half circle and fixed central point and radius. Okay, so that's a brief definition of H2. But now if you have 2 by 2 matrices of determinant 1, namely ABCD in SL2R, then it acts on upper half plane by so-called linear fractional transformation, which is given here. So now you identify the point on the plane with a complex number like this, and then this is a formula. You map this point to that point, and you just check that upper half plane is mapped to upper half plane. I think you can see that the x-axis, that's the real numbers, are mapped to real number. So x-axis is preserved. And what you can check by computation is that this map is not only a map, but also it preserves the metric given here. Okay? So its computation, you can try. With this formula, you can try that this Riemannian metric is preserved. But also, so I'm going to give maybe few exercises in each talk. So here's the exercise. So there are two families of matrices. So clearly they are in SL2R. And first, I suggest you to check what those two matrices do on the upper half plane. Then try to see it really preserves this metric. Okay? You may say those two matrices are very special compared to this ABCD and SL2R, but now you use some little linear algebra. So remember this SL2R is a group. So if any element is given, you try to write that element as a product of those. Actually, there is one element missing, which is another task for you to find. But so this is almost good enough for you to check that any element preserves the distance in the hyperbolic plane. And then this last line says actually not only this SL2R acts on hyperbolic plane, but actually that's the only ones. So any element acts on hyperbolic plane, preserving that hyperbolic metric is in fact given in this form. And as Oshika sensei pointed out yesterday, so there is a center, so you divide it by plus minus identity element, you get a group called PSL2R. So that group really acting on the hyperbolic plane. What's the name? Not faithfully. Oh, I don't. So any element in here acts on the hyperbolic plane non-trivially. Okay. What's next? Okay. So here is a sample claim for which geometry plays some role or useful, which you can see. Okay, so now suppose you have a subgroup gamma in PSL2R and assume it's discrete and torsion free, and then try to see what you can say about this group gamma. So by discrete, I mean I use the action on a hyperbolic plane, namely this gamma acts on hyperbolic plane properly, namely for any point in hyperbolic plane and any number r, there are only finitely many group elements in gamma that maps x to the ball of radius r centered at x. And so I write it in this way, and there are only finitely many such elements. Then you say this action is proper, and I say this gamma is discrete. And torsion free is torsion free. By the way, a discrete subgroup of PSL2R is called the Fuchsian group, and it has been studied for many years. So here's a question I like to answer. What can you say about gamma? Okay, so use geometry. I look at the quotient since PSL2R acts on hyperbolic plane. Therefore, I can go to the quotient space H2 over gamma. But now I use gamma is discrete and torsion free. Actually, this quotient map is a covering map in the usual sense. So this is another exercise to show that this quotient map is a covering map. Therefore, since a hyperbolic plane is a two-dimensional manifold, and the quotient space is also a manifold and two-dimensional. But now there are two cases. The quotient is compact. Then you have a compact two-dimensional manifold, no boundary. And also, since I didn't say it exactly, but here, this element in SL2R preserves the orientation of the hyperbolic plane. Therefore, you get the oriented manifold in the quotient, compact, so it's a surface. And the pi1 of the surface is called the surface group. And now you use a theorem from the covering theory saying that this deck group, gamma, is isomorphic to the pi1 of the quotient. So in conclusion, your gamma is a surface group. Or the other case is that quotient is not compact, still it's a surface. And then here's a little fact, a non-compact surface, its pi1 is a free group. Because imagine you have a surface, but some punctures or disks are removed, so it's homotopy equivalent to a graph. Therefore, the pi1, its pi1 is a free group. So now again, gamma is isomorphic to the pi1 of the quotient. Therefore, it's a free group. So conclusion is that torsion-free discrete subgroup in PSL2R is either a surface group or a free group. Okay, so that's some kind of little argument using geometry to understand the structure of a group. Okay, so I prepared this slide as a variation of the theorem or a fact I just mentioned, and also kind of introduction to the subject of the talk I'm going to talk about. So what about if you have a group gamma in SL2QP? So I put SL2QP instead of SL2R or PSL2R, but I put the same assumption for gamma is discrete and torsion-free. So this QP is for the field of p-adic numbers for p prime. So I don't know much about it, but so QP is another way to complete Q. And so of course one completion of Q is R, so which looks very natural. But there is another way to complete as a topological space of Q, and that's going to be QP. So I remember when I was a freshman taking a calculus course, my teacher said this R, the set of real number, is Archimedean. And he said, okay, if you have two positive numbers A and B, then you can always find a positive integer n so that A times n is bigger than B. And he said it's a very important property or axiom. But it looks trivial. But interesting thing about this QP is it's not Archimedean. So if you have two, its order, so it's positive A and B, you can't find n, so that sometimes you can't find n so that A times n is bigger than B. Anyway, so let's suppose such things exist, and suppose you have a discrete torsion-free subgroup gamma there, and then there is a theorem by Ihara more than 50 years ago, and he says gamma is a free group, always. And Seah saw the paper, and I'm sure he understood it, but also he wanted to, okay, so I remember there is a quote. So Seah says Ihara's argument is combinatorial, but topological approach is more natural. That's what he said, something like that. So what is the approach he took? So he wanted to find, remember the previous argument. So SL2R is acting on hyperbolic space, therefore its discrete subgroup gamma acts on that, therefore you go to the quotient space and do some kind of topology. Okay, here what's missing is a space for SL2QP to act on, and Saya found it acts on the tree. It's example blue at its tree. And anyway, this SL2QP acts on the tree by automorphisms. In particular, if you put a metric on the tree, namely each edge has length 1, then it becomes a metric space, and any automorphism is preserving that metric or distance, so it's by isometries. And now the rest is same. Since gamma is discrete and torsion-free, the quotient map is a covering map in the usual sense, but T is a tree, therefore the quotient is a graph, but pi1 of the graph is always free, therefore gamma is free. So that's the end of the proof. So this is a nice argument. So Saya's observation is that if gamma is free because it acts on a tree freely. Okay. By the way, I also put the definition of the tree here. A tree is, in this talk, a simplicial graph which is connected and simply connected. So namely, no embedded circle in the graph. Then you call it a tree. Yeah. So, well, Saya, I look up the book by Saya, and Saya says also tree is non-empty. So I should have said it's non-empty too. Okay. All right. Oh, okay. And also Saya wrote a book titled Trees, which is readable. So if you are interested, I suggest you to take a look and maybe try to read. So not only he proved he gave an interpretation of Ihara's proof, but also he developed a theory. For example, so SL2R or PSL2R acts on the upper half plane, but he found the invariant subspace for SL2Z. So, okay, I found this on the internet too. This invariant subset on the upper half plane is a tree which is given here. Since it's invariant, it means in particular SL2Z acts on this tree. So that here are some properties you can say. First of all, the quotient is just one edge. So you have, so those are vertices. So there are two colors, white ones and black ones. And actually, white one is for one orbit of the action by SL2Z, and the black ones is the other orbit. And so edge has only one orbit. Therefore, the quotient is just one edge. And also, stabilizer of a black vertex is Z over 6Z. So you only see 3 lines. So it acts by rotation by